Rotatory motion. Rotatory motion. Example of rotatory motion, rotating body. In the figure, the three triangular pieces represent the blades of a fan. A fan. The dots on these triangles are the particles of the blades of the fan. Particles of the blades of the fan. The particles of the blades, they rotate in concentric circles. When the fan is rotating, the particles of the blades, they rotate in concentric circles of different radii. So such motion is rotatory motion. Such motion is an example for rotatory motion. It is one of the forms of rotatory motion. Features of rotatory motion. The particles of the body move in concentric circles. The particles of the body move in concentric circles. The line about which the particles will be rotating is called axis of rotation. The line on which the center lies is known as axis of rotation. The speed of the particles depends on their distance from the axis of rotation. The particles near to the axis of rotation, they will have less speed. The particles which are far away from the axis of rotation will have greater speed, higher speed. But the angular velocity will be the same for all the particles. The angular velocity will be the same for all particles. The speed of the particles on the axis of rotation is 0. For the particles on the axis of rotation, the speed is 0. Uniform circular motion. Uniform circular motion. A particle is said to be in uniform circular motion if it moves along the circumference of a circle with uniform speed. If a particle moves along the circumference of a circle with constant speed, it is said to be in uniform circular motion. Then the angular velocity of the radius vector is a constant. Then its angular velocity is constant. That means the angular velocity of the radius vector is a constant. The velocity of the particle will be tangential to the circular path. The direction of velocity will be tangential to the circular path at any instant. So the direction of this angular velocity will be changing continuously. The direction of velocity will be changing continuously in uniform circular motion. This is possible only when a force acts perpendicular to the direction of velocity situated towards the center of the circle. Only if there is a perpendicular force directed towards the center, then only the continuous change in direction of velocity is possible. Consider uniform circular motion. Suppose in uniform circular motion, the radius vector OP is sweeping. It is rotating with a constant angular velocity omega. With a constant angular velocity omega. Suppose the time taken to rotate from the direction of OX to OP is say t. Then the angle between OP and OX is theta is equal to omega t. If the radius vector rotates from the position OX to OP in time t, then the angle between them theta is equal to omega t. Now the radius vector r or r bar can be expressed as two components. So one is Ox is say x-axis and Oy is y-axis. Then the component of this vector along x-axis is r cos omega ti. R cos omega ti. The component along y-axis is r sin omega tj. R sin omega tj. So the vector r bar can be written as r cos omega ti plus r sin omega tj. The vector r bar can be written as r cos omega ti plus r sin omega tj. The velocity of the particle v is equal to dr by dt. The velocity is dr by dt, but r is r cos omega ti plus r sin omega tj. So v becomes equal to r omega into minus sin omega ti plus r omega into cos omega tj, because the derivative of cos omega t is minus omega sin omega t. The derivative of cos omega t is minus sin omega t into omega. The derivative of sin omega t is cos omega t into omega. So it becomes r omega cos omega t j. So V is equal to r omega into minus sin omega t I plus r omega into cos omega t j. From this relation we can obtain the acceleration from the relation A is equal to dv by dt. From the relation A is equal to dv by dt we can obtain the relation for acceleration. We have derived the relation for velocity V is equal to r omega minus sin omega ti plus r omega into cos omega tj. A is equal to acceleration is equal to dv by dt. So A is equal to r omega square into minus cos omega ti, because sin omega t derivative is omega cos omega t, hence we get r omega square into minus cos omega ti. Similarly, cos omega t derivative is minus sin omega t into omega, hence it becomes minus r omega square into sin omega t into j. So the acceleration is r omega square into minus cos omega ti minus r omega square into sin omega tj. You obtain these derivatives in mathematics. So mathematics students can follow easily, and biological students they have to memorize these relations. So acceleration A is equal to r omega square into minus cos omega ti minus sin omega tj, or it can be written as minus r omega square. A is equal to minus r omega square in scalar form. R omega square is magnitude, and the direction of this acceleration is opposite to the direction of radius vector. R omega square is magnitude and minus is sign. This sign indicates it is acceleration is opposite to the direction of radius vector. So the acceleration is towards the center of the circle, since radius vector is from O to the circumference of the circle. Centripetal force. The acceleration is obtained as minus r omega square. So force F is equal to ma, where m is mass of the particle in circular motion, uniform circular motion. So F is equal to m into r omega square if we consider acceleration as r omega square. F is equal to mr omega square. Or acceleration can be written as v omega. So if you write acceleration as v omega, F becomes equal to mv omega. Acceleration can also be written in the form v square by r. Hence the force becomes equal to mv square by r. This force will be in the direction of acceleration, that is towards the center of the circle. Hence it is called centripetal force. This force is responsible for the change in direction of the particle in uniform circular motion. So whenever a particle is in uniform circular motion, it will have acceleration towards the center, and a force is directed towards the center, and that force is centripetal force, whose magnitude is given by mv square by r, one of the forms. Work done by centripetal force. The relation for work done is equal to, W is equal to F dot S, force into displacement, dot product of force and displacement. So W is equal to Fs cos theta. Here theta is 90 degrees. The angle between displacement and force is 90 degrees, and cos 90 is 0. Hence work done by centripetal force is 0. F into S into 0 is 0. Hence work done by centripetal force is 0. Centrifugal force. As soon as the centripetal force is applied, immediately a force will set in due to inertia of the body in circular motion. Due to inertia of the body in circular motion, a force is set in away from the center of the circle. A force acts on the body away from the center of the circle due to its inertia. This force is called centrifugal force. The magnitude of this force is equal to the magnitude of centripetal force, but its direction is opposite. In the figure, you notice centripetal force towards the center and centrifugal force. CF indicates centrifugal. It is away from the center. So the relation between them is written as FCF is equal to minus of FCP. The centrifugal force is equal to minus of centripetal force, but their magnitudes are equal. Relation between angular and linear physical quantities. Relation between angular and linear physical quantities. If you consider a circular arc of length S with radius capital R, consider a circular arc S. The radius of the circular arc is R and the arc subtends an angle theta at the center. Then we have the relation S is equal to R theta. Arc length is equal to radius into angle. S is equal to R theta. The speed or velocity is described as ds by dt. Rate of describing the distance is speed. Rate of change of position is velocity. So it is written in the form v is equal to ds by dt. But S is equal to R theta, hence d by dt of R theta. Velocity is d by dt of R theta. R is a constant, so v is equal to R into d theta by dt. R into d theta by dt. But d theta by dt is angular velocity omega. Hence, v is equal to R omega. V is equal to R omega. This velocity v is tangential to the circular arc. This velocity is tangential to the circular arc. Relation between linear acceleration and angular acceleration, or tangential acceleration and angular acceleration. We have the relation for acceleration a is equal to dv by dt, rate of change of velocity. A is equal to dv by dt. It is equal to d by dt of r omega. D by dt of r omega. Since r is constant, a is equal to r into d omega by dt. R into d omega by dt. But d omega by dt is angular acceleration alpha. D omega by dt is angular acceleration alpha. So a is equal to r alpha. The direction of this linear acceleration is tangential, and the direction of angular acceleration will be perpendicular to the plane contained by the circular arc.